a great pleasure this week to have as our first speaker, Richard Montgomery, who's going to talk on a solution to Erdős and Hajnal's odd cycle problem.
Okay, thank you very much. And thank you for the invitation to talk. I'm going to talk about different cycle lengths in graphs, and all of this is joint work with Hong Lu at the University of Warwick. Okay, whenever I say incidentally different cycle lengths in graphs, I don't want to consider how many cycles there are of each different length. So all I care about is, given a certain length, are there any cycles of that length? So to find any cycles, I need to impose some conditions on the graph. And perhaps the most natural one is to impose an average degree condition. So if I tell you the average degree of a graph and absolutely nothing else, nothing to do with the number of vertices or any structural properties, then is it possible to say anything about its different cycle lengths? And of course, such a graph, it could be bipartite, so it might have no odd cycles. So if I'm interested in odd cycle lengths, then maybe a natural condition to give you is to tell you what the chromatic number instead is of a graph. Now, I'll just use little notations. So we have the cycle space of a graph, C of G, is the set of integers, which I can find a cycle of that length. And then I'll add a subscript, odd into the subscript, and just consider the odd cycles in a graph. So already I've split what I'll talk about the problems into both even and odd cycles. And I'll also consider two different styles of questions. So to give you just a picture of what will come, here's a rough table. So for both even and odd cycles, I want to consider some sort of notion of density of the cycle space. And then I want to have a look and see if I can find specific cycle lengths in the cycle space. And as I go on, I'll give more detail on some really explicit questions here. Okay, but I'll start in the top left quadrant where we know the most around it, right? So for the density of the cycle space, it's, for example, very easy to show that the number of different cycle lengths is at least linear in the average degree of a graph, as long as there are some cycles. But those cycle lengths could be really long, so this cycle space could be really sparse. And more than half a century ago, Erdős and Hajnal suggested the following density function for studying the density of the cycle space. So particularly taking the sum of the reciprocal of the cycle lengths of a graph. And they asked, can you make that sum arbitrarily large by making the chromatic number of a graph increasingly large? And they also suggested that maybe actually you don't need the chromatic number, maybe just the density. Sorry, not the density, the average degree. Making it large should be sufficient. So how might we expect this function to grow? We're just asking that it goes to infinity, but how fast might it need to grow? Well, if you look at the complete bipartite graph with average degree d, then obviously it has all the possible even cycle lengths for up to 2d. So if we do our calculations, then we get around 1/2 of log d. And in 1975, Erdős conjectured that there should be an asymptotic lower bound over all graphs with average degree d. So any graph of average degree d, this sum should be at least about 1/2 log d. And indeed, we know that this is the right rate of growth for optimal universal lower bound, thanks to Jarvis, Komlosh, and Semeridi in the 1980s. So they proved that the sum does indeed is at least linear in the logarithm of the average degree of a graph. Okay. So that's very nice and answers the question of Erdős and Hajnal in the 60s above. Okay, so we're now comparatively well informed about the density of cycles and graphs. What about trying to find specific cycle lengths instead? Well, as I'm very sure you know, due to the famous result from Erdős in the 1950s, if I fix a k, then the chromatic number can be arbitrarily large, and yet I don't have a cycle of length k, or even any cycles up to length k. So that's a non-starter. But instead, what if I have a sequence of numbers here, sigma 1, sigma 2, and so on, by imposing an average degree condition or a chromatic number condition? Can I guarantee that one of those cycle lengths must be in the cycle space? So I'll bring back up the table from the first real slide of the things I want to consider, and let's fill in a little bit more detail. So for the even cycles, I want to impose an average degree condition. For the odd cycles, I want to impose a chromatic number condition. And if I'm looking for a specific length, then I want to find some length within one of the sequence sigma 1, sigma 2, sigma 3. And roughly speaking, so we know that the sequence of integers, as long as the average degree is at least 2, will have at least a cycle length. But how sparse can we make that sequence and still find something? So I'll make these questions even more explicit. So I'll just expand that previous table that I had. I already discussed the upper left quadrant there. So we have this result of Garvis-Common similarity and the conjecture of Erdős. And then as an example of a sequence, you might want to find a cycle length Here's a question of Erdős from the 1980s, just an example of some of the ones he asked. Is there some d, just some constant d, such that if the average degree of a graph is at least d, then I must have a cycle length which is the power of 2. And now in the right quadrant, so as I go through these quadrants, instantly we know less and less. So in the upper right quadrant now, what about the odd cycles and this density function? Erdős and Hajnal asked in the 80s, the problem is the title of this talk, does this sum, if I just restrict it to the odd numbers in the cycle space, some of the reciprocals diverge as the chromatic number of G gets large. And down in the bottom right quadrant, less asked, but let's take as our example sequence. Can I find a cycle which has a length which is a prime number just by imposing some chromatic number condition on G? So as I've set this up, it looks like two very sort of separate halves and problems. What will happen is I'll talk about even cycles and the results I have with Hong, and as I'll show you, they can be used to prove results about odd cycles. So most of the difficulty is actually in the stuff we do for even cycles, and then it's not too hard actually to work to odd cycles from there. So as I said, I covered the top left-hand quadrant. So what do we know about specific sequences in the bottom left quadrant? Let's have a quick definition. I'll say a sequence is unavoidable with high average degree if by imposing some degree condition, then I guarantee one of those integers as a cycle length in my graph. So my question from the previous slide just becomes, are the powers of 2 unavoidable with high average degree? As I said, we know the integers are unavoidable with high average degree. That's trivial. How sparse a sequence can we get? Well, in the 1970s, Bolabash answered a question of Burr and Erdős and said, well, essentially, we can take this to be arbitrarily sparse. And in particular, if the sequence is an arithmetic progression, which contains even numbers, then it is unavoidable with high average degree. And then much later, Verstraete in 2005 gave a non-constructive proof and showed that there is some increasing sequence with density 0, which is unavoidable with high average degree. Okay. So later in work of Benny Sidakov, Verstraete got really close to showing that there are lots and lots of sequences which are unavoidable with high average degree. So the results are quite complicated written down, so I'll write down a sort of simplified version of it. So if a sequence contains even numbers and is exponentially bounded, then it is unavoidable with high average degree, except in perhaps really, really sparse graphs. So here exponentially bounded is what you think it means. Just there's some constant for the sequence so that each subsequent term is at most that constant times the previous one. And exponentially sparse, we have that the average degree is at most the exponential of the iterated logarithm function of the number of vertices. So really exceptionally sparse graphs. So as well, I'll now talk about some of the results of Hong and I on even cycles. And I'll bear in mind that I really want techniques which work in really sparse graphs. So our techniques do work in all graphs, but in particular, the challenging part is to definitely close this gap. And what Hong and I can do with even cycles is, given sufficiently high average degree, can use a constructive proof to construct lots of cycles with different lengths and to find an interval in which we can construct a cycle of each even length in that interval. So soften you up, and here is the result. So as I said, if the average degree of a graph is just sufficiently large, then I can find some R. And in particular, this R is the parameter for this interval in the cycle space in which I can find every even integer. And the parameter R is almost as big as D, just a polylogarithm function below it. Okay. And that's great. How does it relate to what we had in the previous slide? Well, if we're looking for this density function, then I just need to sum up the reciprocals of such an interval, of even numbers in such an interval. And that's approximately 1/2 times log R. So from the lower bound in R, it's definitely 1/2 log D. So we get this universal lower bound that was conjectured by Erdős asymptotically. So because our top left quadrant, the density of the cycle space, what about these sequences and specific cycle lengths? Well, from this result, if a sequence is going to be unavoidable, then I can just show that eventually it must appear in every such interval if it has even numbers. So if an even increasing sequence eventually appears in each such interval, log it to the R, then it's unavoidable with high average degree. And in particular, well, this shows that really lots of rather quickly growing sequences are unavoidable, but it shows that all exponentially bounded sequences are unavoidable. And one of the key things with this theorem is that the sort of more technical theorem that's just sitting right behind it, as it were, allows us to use it to find odd cycles as well in a way that couldn't be done beforehand. So this allows us, without actually much more work, to make a lot of progress on odd cycles as well, where really not very much was known before. So back to odd cycles, and here's a very similar definition about how you could be unavoidable with high chromatic number. And that's true if there's just some constant, so that if a chromatic number of graph is at least k, then you must contain some cycle length in that sequence. And here I'm really thinking about odd numbers. And my question before becomes, is the sequence of prime numbers unavoidable with high chromatic number? So not too much is known about the density or anything of the odd cycles in a graph. So due to Garfus, we have a bound to at least show there are some odd cycles in a graph based on the chromatic number. Again, we have a result of Sudakov and Fish-Strait from 2008 that finds instead some consecutive integers and hence some odd numbers. But again, just as before, we don't have any bounds on what size these are, so that this cycle space could be really sparse still. And we also have this result I'll mention again of Benny Sudakov and Jacques Fish-Strait, which says that, well, we have this density function that we want, the sum of the reciprocals of the odd cycle lengths, and it does go to infinity. But as well as having a similar relationship between the parameter and the size of a graph G as we had before, this exponential iterated logarithm function, we also can't use the chromatic number, but a relaxation of the independence ratio of a graph instead. Whenever it comes to specific unavoidable sequences, we couldn't find any results at all. So as I'll show you, you can move from our more technical result on finding odd cycles to get more technical result from getting even cycles to getting odd cycles. So we have a very similar theorem where we impose instead a chromatic number condition. The interval looks a little different and it's not as wide, but still, if we have chromatic number k, then for some r, we can find every odd integer in the cycle space between r and r times k to the 1 minus epsilon. And this is enough to give us good bounds on the density function we had before. So if we do the same calculation, then the sum of the reciprocals of the odd cycle lengths is again about 1/2 k, which again you can show is tight, and indeed is tight because yes, you're only summing over odd integers, so you just look at the complete graph. And again, for exactly the same reasons before, fewer sequences can be shown with this result to be unavoidable with high chromatic number, but still ones that go much faster than exponentially bounded sequences. And then again, we knew that prime numbers therefore are unavoidable with high chromatic number. So before I move on and try and talk as much as I can about how one might prove these sort of things, I'll just summarize the main things I've shown you. So for even cycles, Hong and I were able to show this conjecture bound of Erdős, and also that the powers of 2 are unavoidable with high average degree. And we also get an asymptotically optimal lower bound on this density function of the reciprocals of the odd cycle lengths based on the chromatic number. And we can also show high chromatic number, we must have a cycle which is a prime length. I put 21 plus on these. We put the paper on the archive at the end of last year at some point. Okay. So I don't see anything in the chat or anything, so I will put on and talk a little bit about the proof. As I said, the crux of it is making sure that we're using techniques that can work on really very sparse graphs. And sort of that kind of guides what sort of techniques we might use. So we're going to use a form of expansion introduced by Commerce and Semery to find subdivisions in sparse graphs in the 1980s. These techniques that both Hong and I had worked on individually and together. And we're going to use a very constructive approach. So lots of drawing on the blackboard, and Hong and I spent a long time drawing potatoes and paths between them and so on. So the constructive approach that we're going to use, like our sort of tool of construction to think about this in a simple way, is to say that we can connect pairs of vertices with short paths to create some structure in which we can adjust the length of cycles. So I'll give an outline of the rest of the talk I want to talk about. Oh, just in passing, lest I forget. So you can always assume that the graph is bipartite. So I'm going to talk about the even cycle case. Sorry, so I'll assume it's bipartite and that I have some minimum degree condition. Although I'm not sure I'll actually go into enough detail to make that important. But okay, so for the rest of the talk, I'll talk about constructing even cycles in as simplified a setting as I can give you and draw some pictures. And then I won't be able to put it off any longer, so I'll give you some Commerce Semery expansion if you haven't seen it before, but I'll keep it as simple as I can. And then one of the main things I want to talk about is how to move from constructing these even cycles to getting odd cycles, because as I say, I think this is relatively straightforward. And then if I have time, I'll just mention kind of the key technical problem that we had to get round whenever we were doing this. Hong and I think we started talking about this about 5.5 years ago now, something like this, some long time ago, in relation to constructing subdivisions in which every edge is subdivided the same number of times, so, which is a problem of Thomason. And we worked on it off and on over the years and various things, and we really only cracked it a year ago or so by very specifically getting around this problem we had. So I want to highlight that if I can. But for the moment, I'll try and keep things as simple as possible and have a nice simplified setting for what I want to do. So what I want to do is to be able to find a path of this specific length between any two vertices, x and y, in a graph G. And then I can just apply that with x and y being just some edge in my graph, and I'll get a cycle with a specific length. So this is a property that I'm desperately trying to work towards. Let's assume that I can do something that is much easier. So let's assume that I can find a path between those two vertices x and y, and it's just reasonably short. That's the only thing I want to impose on it. That's not a very strong property, so let's assume that I can do it vertex disjointly between lots of vertex pairs in my graph. Okay. So just taking this simplified setting, this property, we can take lots of different vertex pairs and vertex disjointly connect them with short paths. Can we start to vary the lengths of the paths and gain some control over their length? And this is actually relatively simple to do. So I've given you some numbers or some letters in case it helps, but otherwise do ignore them. But if we have n vertices, and we'll aim for paths with length, something that's polylogarithmic in n. So by just taking any two other vertices in this and connecting them with a couple of paths, we'll definitely find some short cycle. So I can pretend to have this. I can take this cycle with length that moves 2m in my graph. And now if I take two almost opposite points on this cycle, I can connect them both to x and y with short paths again, so they have length that moves to m. And what have we done? Well, so there are two paths between x and y here. So for some L, I have two roots from x to y. I can either go down on this length 4 side of the circle, or I can go up over this length 6 of the circle. So just incidentally, my assumption that I was bipartite means this cycle is even, so I can get a change in length of 2 every time I go up or down. Okay. So that's a really good start. I've developed a little bit of flexibility between these two. So let's keep going and build in some more. I've just repeated here this property of connecting lots of vertex pairs. And let's now take L to be some larger polylog, if you want to think of it like that. So we can now use this to build up an xy path with length either L or L plus 1. Where the difference only depends on the parity between x and y, so whether x and y are in the same class in the bipartition or not. So I'm going to do this. I just repeatedly do what I did before. If I take m different vertex disjoint cycles here and join them into a path from x, again joining the pairs of vertices that are almost opposite, then I can join those into a path, and I can lengthen that until the shortest length of the path I have is in this interval from L minus 2m to L minus m. So what I mean is to take the shortest path through these possible cycles. I have this property of connecting pairs of vertices, so I can continually take more extra vertices and connect them with a short path. And it will look like so. And I keep doing this until I'm as close to L as possible, which is what I'm aiming for, but I'm below it by at least m, and it moves to m. And then I finally use my property to connect it in through to y. Great, so this shortest path length is now in the interval L minus 2m to L. And now all I need to do is lengthen it in steps of 2 by taking these cycles and taking the long way round instead of the short way round until I have exactly length L or length L plus 1. So this is our construction. I think that's, yeah, the only ones I've put in. So this is our construction. And the challenge is just carrying this out in the in every possible graph or a subgraph of every possible graph using the expansion that I will talk about. So I can't avoid any longer, so I'll tell you some more details about the expansion. Forgive me if you've heard them before. So this first thing that I put up, so all of this is due to Comlish and Semerady. This is just a corollary of their work that I've just put up to demonstrate that it's a way of getting the property that I talked about before, being able to connect pairs of vertices by some path that is not too long. And of course, you can't expect to connect every pair of vertex in every pair of vertices in every graph. It might be disconnected. But what they proved was that every graph G contains some subgraph H, which actually is about as dense, has average degree not much smaller than G, in which every pair of vertices is connected by a path, which has length at most some polylog in the size of H. So we're going to use an expansion condition that gives us this nice property. The definition of expansion we need to take is going to be really weak so that we can find it in a subgraph of every graph. So given some parameters epsilon and k, it simply says that for every vertex subset, which is not too small, and we're thinking of k as a constant here, incidentally. So this does apply to small sets. And has size up to the size of h over 2, so most half vertices, then the out neighborhood, the exterior neighborhood of that set U, has size at least some expansion function times the size of U. If you've not come across this particular style of expansion but have in random graphs, say, then this is a really weak form of expansion. You're probably used to seeing a 2 here for poser rotation or something bigger if you're maybe embedding trees or something. But here we have this function. In particular, to note, it does decrease as U increases.
Richard, there's a question in the chat about the size of H.
Probably want to say the size of H. Yeah, I'm probably being a little informal, I'm afraid, with this result of Comlish and Semerady. Yes, this graph probably should be at least of some size. Yes, it depends on the parameters of this expansion, but yes. Okay, I won't stop to think whether I can make this true by hiding everything in the big O term or not. Okay. Yeah, so we have this expansion condition, and it's really weak, and it's sublinear, which I will complain about later to you. What do I have here? So here's the important result. So there exists some epsilon, some between 0 and 1, such that every graph G with average degree at least 8D has a bipartite epsilon 7 times D expander subgraph H with minimum degree at least D. Maybe we want D to be a certain size as well. I shan't that. Probably not by making epsilon very small. Okay, but the key point here is that in every graph, just based off some average degree condition, we can look within it and find a bipartite graph that satisfies some expansion condition, however weak, and has a minimum degree condition. And that's what we're going to work with. So I have mostly the pictures here just to illustrate how you can use expansion. This goes exactly as you would wish. If you're an inverse X expander with some minimum degree condition, then given any pair of vertices X and Y, it's very easy to connect them with a path with length, which is polylogarithmic in N. So this log to a third term, incidentally, which is my background, comes from this log squared term playing with us in here. So yeah, and this is exactly what you expect to do. We take X and Y and we use our expansion condition. Well, we first use our minimum degree condition. Then the minimum degree condition means that if I expand this little set here, then it satisfies the lower bound in the condition for expansion. So we can start expanding, and we can expand, and then eventually these wizard hats of expansion will intersect, and then I find a short path between these two vertices. Okay, so this is a rather easy property, and the difficulty in our construction is being able to connect pairs of vertices while avoiding other things that we've constructed already. And that's where all the difficulty comes in. So yes, as above, pairs of single vertices are really hard to connect vertex disjointly if I find some other stuff already in the graph, some other of these cycles, and I wish to find more cycles and then connect them up as I showed them. So instead of finding cycles for our construction, what we do is we find the cycles and we find other subgraphs as well, which are larger than the cycle, and will help us join everything up. And we call them adjusters, and they look a little bit like this. So instead of just X and Y, we have some large subgraph, which has some small diameter. So that if I can expand X or Y while avoiding the rest of the vertices in the cycle, and also some other vertices, then I can do this with different adjusters, expand them and connect them together to do this chaining up that I had on a previous slide. Finding many of these is the main challenge behind our work. So I won't go into this main challenge anymore for the moment. I'll just say that finding this expander subgraph H and G, which can be much smaller than G, we can find it. Then applying our construction using the adjusters gives the following result. So this is the technical result I mentioned that was behind the main result on even cycles that I said. So what it says is if the average degree of a graph is sufficiently large, then I can find within it a connected bipartite subgraph and some parameter L of H, such that the following is true. And it just means this property is that I can take distinct pairs of vertices X and Y, and I have this large interval based on the parameter from L up to L times D to the 1 minus little of 1. And I can find a path of length R in H between X and Y. And again, if parity permits, so if they're in the same class in a bipartition, then definitely I want to find an even path between them. And if they're indifferent, then odd. Okay. So this is our technical result. It's strong enough to let us then quite naturally move to finding odd cycles instead of even ones. So we're really good at finding bipartite graphs which have this boxed property. So suppose we could find the following, which is kind of like an odd cycle of bipartite graphs. We're thinking of it as that. So suppose we could find the following 5 bipartite graphs, H1 up to H5, which only intersect on the vertices. I've drawn these black circles, and otherwise a vertex disjoint. and such that they satisfy this box property, each with its own parameter L of I. So between any vertex pairs in these different graphs, each of I, I'm really good at finding different length paths. And as I've drawn it, you'll observe that if I find any path that goes around this cycle within the subgraphs and comes back to the start, sort of with winding number 1, then it's going to be an odd cycle. So I can use this property and take these shared vertices, vary the length of a path between the two shared vertices in H1, and then between two vertices in H2, H3, H4, and H5, and so on. And I get an odd cycle because of I've chosen these vertices and these constructed ones. I haven't, just as an example, they're not always on the different sides of the bipartition, but if you count round the parities, you'll get an odd cycle. So I can use this box property to vary the lengths of paths, and whenever I put that together, I get many different odd cycle lengths. Again, this is something of a dream simplified scenario that is really nice. We probably can't find such a thing. In particular, this property that these shared vertices are the only vertices in which these graphs intersect is quite a strong property. But let's see what we can find. So this again just repeats the slightly more technical result I had on the last slide. So using this result, what we do is iteratively pull out as many edge disjoint connected bipartite graphs, HI, which satisfy this box property. So it's really easy to connect vertices with lots of different paths. From that result above, you can deduce that if we started off with a high chromatic number, then what you've removed, the union of those bipartite graphs, must also be high, and in particular, it must be at least 3 in this case. Otherwise, in what remains, it has chromatic number at least D, so average degree at least D. So I could find another one of these bipartite graphs. So we know that the union of these graphs, like before, the union of these HI contains some odd cycle. The graphs just may not be as nicely behaved as these ones. So you have some odd cycle. And just very roughly, if you just take a minimal such cycle, then you can prove that, okay, they might overlap, but they won't overlap too much. And if you only replace some of the edges using the box property, maybe on every second edge, then the paths that you replace won't intersect with each other. But these are just technicalities, and really it's not too hard to find many odd cycles from there. While I'm on this slide, so it's a very natural condition, the average degree condition. The chromatic number condition to get odd cycles is less obvious. And indeed here, the property that we're using, as you can see, is more that a graph kind of robustly has chromatic number at least 3. So if a graph has a property that I can't remove a bipartite graph with average degree at least D, and not be 3 chromatic anymore, then this is sufficient for this to work. I probably messed up my words there, but some condition like that, rather than anything about the chromatic number needing to be more than 3. So that's how we move from even cycles to odd cycles. So I want to say a few words on the technical issue of sublinear expansion. So we're trying to construct things using this really sparse expansion. And we want to construct these adjusters, as I showed you before, these cycles with the 2 triangles. And if you're just finding one adjuster, then with the parameters we want, it's relatively simple to find. If you start with a minimal cycle and you expand from X, then you're not going to encounter too many vertices very quickly from the cycle, otherwise you would have a shorter cycle. So you're going to expand to some large subset, which is quite small diameter. So you naturally get this. It's a bit harder to get a second one, but it's not so hard. The difficulty is finding lots of these. So in all of our constructions, we find things, we gather them together into some vertex set W, and then we try to find another adjuster in the graph with W removed. And this is much harder. So the natural way to do this is to just try the construction above again. And it works if you get the sets that you're finding, if they still expand nicely. So we can try the same construction, starting off with a short cycle and expanding it. And if it goes wrong, we end up with a bad set, which doesn't expand in this graph with W removed. And then we repeat this, and we find many disjoint bad sets. And until now, we haven't got any contradiction. It's fine. These bad sets may not expand in H minus W, but they still expand in H. What we'd love to do is be able to put these sets together to get this big bad set, which is much bigger than W. So it should still expand, even after we've removed W from the graph. So if it doesn't expand, then I get a contradiction. But this is not so good because, in this case, because of the sublinear expansion, I can put together bad sets which don't expand because they're quite small, so I'm asking a relatively big expansion condition for them. But whenever I put it together, they still qualify as expanding within the bigger set. In particular, I've repeated this requirement for expansion again, so that you can see that this, to remind you that this function is decreasing as the size of U increases. So aside from this problem of sublinear expansion, my problem now is that I have this really specific thing that allowed us to crack this problem that I'd love to share with you. But I'm aware it's kind of a little in the, and it's really not too hard either, I'm convinced by. But it is a bit technical, so I'm just going to say some words, and I just hope it will. If you know lots about this expansion, then that's great. If you don't, then I think we'll just hope it sticks in your head. So if you ever find yourself constructing things and come across this problem, then you might want to look at our paper. So again, this function decreases, it increases. So we have bad sets, so we put them together, but their union does still qualify as expanding. So our strategy is we just have to sort of very carefully set up the situation so that we have very many bad sets. So I know I have lots of bad sets which have the same size. And make sure that the bad sets don't really expand hugely into W. And this will allow me to find many bad sets which have the same size, but also that they have the same neighborhood in W. And then I can combine the right number of those bad sets to be larger than the neighborhood in W, but not large enough to decrease this function, this expansion function a lot. Oh, sorry, yes, there's a typo in this. Sorry, so this is a vertex set U of the vertex set in H rather than G, if that helps answer the question in the chat. This was for all vertex sets in the graph H, which satisfy this size condition. Okay, so I don't want to go on for too much about this strategy, as I say. I just wanted to stick in your mind a bit. So we get a contradiction. It just takes a little finesse to stick the right number of sets together, so that instead of beating the size of W, I just have to beat the size of their neighborhood in W, which is the same for all those sets and which is smaller. And this function behaves badly, but it behaves badly very slowly. So it's not that sublinear. So we can just about get around this problem. Okay, let me finish by just giving you an idea of the limitations of our methods and then some open questions. So from all these constructions that I used, there are limitations on the expansion so that we can find it in every graph. This comes out with connecting vertices with length by log cubed n. So even though you could make it various bits of the argument I sketched out more efficient, you still get around this problem that you're just constructing things with log cubed n. So how quickly increasing sequence could we hope to prove is unavoidable with high average degree? In our paper, I think we prove it with a 10th here instead of this third. The third is kind of a hard limit using our methods from the log cubed that comes from the expansion, as I say. But on the other hand, if you're picking random graphs that have diameter about log n, multiplied by some constant, then you might think actually we should be able to replace that third sigma I to the third with some epsilon times sigma I for some small epsilon strictly bigger than 0. The bounds that we give for the average degree, they always need to be at least a constant. The constant isn't crazy big. We just really need logarithms to be small compared to n, log n to be small compared to n. But we're still a long way off something that could be optimal. So in particular, there's this conjecture of Erdős and Hajnal that every graph of just minimum degree at least 3 contains a cycle whose length is a power of 2. So our minimum degree that we get is, we haven't worked it out, but would be much, much bigger than that, and there's no hope of getting it down to 3. And then I'll mention there's a whole sort of swathe of similar questions that you could ask if you're interested in the length of induced cycles in a graph instead of just the cycles, so the holes in a graph. These are all from a paper of Scott and Seymour on chi-boundedness, so a survey on chi-boundedness. And you're looking for, you need more conditions than just the chromatic number, but maybe by relating it with the clique number, you could guarantee lots of different lengths of induced cycles. These seem all rather difficult. So I believe Scott and Seymour have some result that's roughly the analog of the result of Bolobash on unavoidable sequences being unavoidable with high degree if they have even numbers and come from an arithmetic progression. Other than that, they seem to be very difficult questions. Yeah, and that's all I have. So let me just thank you for your attention and for coming along. Thank you.
Richard, thank you for a lovely talk. It's wonderful to see some of these old problems disappearing. Just to comment on the last thing you mentioned.
Yeah.
So we have results when for triangle-free graphs. So that the general chi-boundedness is very hard, or seems very hard to us. So I had various questions, but you actually answered pretty much all my questions in the talk. Every time I had a question, that you then in the next couple of minutes answer it. So let me invite other people to ask questions. Please do signal in the chat or raise your hand or wave or whatever works.
Okay.
Noga, please.
Yes, so to me also, some of the questions I had, you answered them already, but I wonder, so there is this final conjecture that the minimum degree at least 3 guarantees a cycle of length power of 2. I guess if is there something similar for which a chromatic number guarantees a cycle of prime length? So again, not that I care specifically about this, but are there any constructions that give some non-trivial lower bounds?
I haven't seen any.
So it could be that chromatic number already 3, 4, 5.
Yes, yeah, it could be something really. I suspect it probably is something, though. I just picked out the prime numbers as an example. There's not really much in the literature about. I think Erdős mentioned prime numbers as an example sequence in passing.
Okay, and another question. So I wonder, for odd cycles, how important is a chromatic number? So suppose I only assume that the graph contains one odd cycle and is highly connected, and the average degree is big. Could this be enough already for most of the results about lengths of odd cycles? Because if the chromatic number is big, then you can always make it highly connected if you want, and of course the average degree is big. So somehow the natural minimal assumption is the one odd cycle, high connectivity.
Yeah.
But maybe it's not enough. I just wonder if for your proof this would be enough.
I think perhaps that it depends what you mean by high connectivity. I think if you were asking just for high connectivity, at least some constant, then it's probably not enough. Is my guess for a lot of these questions for getting more odd cycles.
I see.
It seems to me like you could make this, your triangle or something very far away in the graph.
I see, yeah.
And make sure that any odd cycles you have to be really big, perhaps. I'm not sure.
I see. Okay. Mm-hmm. Thanks.
Interesting.
Richard, there's a question from Agalos in the chat.
Oh,
so if you have a sequence where the sum of reciprocals diverges, is it unavoidable?
I have no more information, I think, to answer that question than you do from the results that I've stated. So we can show for my last slide that any increasing even sequences with for each I, the next one is by exponential, the previous one to a 10th instead. So I suspect so, yes. But I wouldn't like to on the spot work it out. Our results are definitely weaker for the odd cycles, but still just saying the exponentially bounded sequence is kind of underplaying it a bit. We can still get quite fast growing sequences. So I suspect it probably is enough to say such sequences would be unavoidable.
Thanks.
Actually, one more question. So I know you haven't worked it out, but so for the Erdős and Hajnal conjecture that the minimal degree 3 gives a power of 2, so you have some degree that works. You have some sense of very vague order of magnitude. So is it absolutely gigantic, or is it something kind of humanly?
Other than non-regularity, I really wouldn't like to guess. I can't even remember what constants come out of the Commerce and Semrady expansion. So definitely not anything even impressively sounding low, I think. Like, so not in hundreds or probably even thousands. That's my guess. But millions is probably more reasonable.
But something that wouldn't take long to write down if you knew what it was.
Yes. But something I wouldn't like to work out or write down still.
Is it any easier if you assume that it's a regular, the graph? So let's say a cubic graph?
Maybe not a cubic graph, but the problem is definitely easier if you assume it is regular, possibly. Oh, wait. I'm speaking. Well, what is true is that if we knew the expander subgraphs that we find were regular, then this would have solved essentially all the problems. A lot of it is in different cases, depending on whether you have high degree vertices and not. So it would definitely be helpful if it was regular. I think with our methods, it wouldn't make it any easier in general. because you could just construct some large regular graph, which some high irregular subgraph, which our methods would focus in on, and then do the construction within that. Yeah.
Okay, if there are no more questions for now, maybe this is a good point to pause and thank Richard. So thank you again, Richard, for a fantastic talk.